So last time we introduced or reviewed this Bloch theorem in elementary solid state to expand the energy bands, and today we will take advantage of this Bloch theorem and show that electrons in a weak periodic potential were from, again, energy gaps between, say, the valence band and conduction band. And we will solve for the Schrödinger equation for a single electron in a weak periodic potential that we introduced last time. But we know that the electrons under such a weak periodic potential actually behave as this Bloch theorem describes, that the electron wave functions carry this e to the I little k dot r with the electron momentum k, and times the periodic function uk of r, which could be rewritten in terms of a summation over this reciprocal lattice vector capital K, and inside the summation we have this coefficient c little k minus capital K times e to the minus I capital K dot r. And you can show that this stuff inside this orange bracket satisfy this periodic properties of this function u. And this is our starting point. So electron under a periodic potential should behave like a Bloch state, where this wave function carry this periodic function of u on top of this plane wave. So you could actually plug in this electron wave function following this Bloch theorem to the Schrödinger equation for that electrons under a periodic potential, and we introduce this periodic potential u both in real space and in Fourier space, and then after you plug in the Schrödinger equation, you get this eigenvalue equation, and you could simplify this notation by defining this free electron dispersion epsilon 0, which is h bar squared k squared divided by 2m. And we should solve for this eigenvalue problems for the electrons in a weak periodic potential. Okay, so we know that there are many degenerate solutions satisfying this equation, and this little I and little j represent such a kind of degenerate solutions. And in particular, we could just look at two free electron levels which are almost degenerate as plane wave solutions like this, and these two electrons show the dispersion relations as quadratic form, but they are shifted by this reciprocal lattice vector as function of a capital K, and we could actually just study these two different cases when this k equals to k1 and k prime is equal to k2, or vice versa when capital K is actually k2 or k prime is k1. So these two parabolas are centered at two different reciprocal lattice vector k1 and k2, but they have intersection right here near this this boundary, and this intersection represents that this electron states centered either k prime or k are degenerate. So these two states have the same energy, and we call these states degenerate states. So we consider two degenerate plane wave solutions of these free electron levels as possible solutions from this eigenvalue problems, but they are not exactly degenerate because we have not included the potential yet. Okay, so these are these two free electron levels that are degenerate at that point. But the important message here is that the periodic potential U is going to lift this degeneracy right at this point, and as we can see in just a moment. So if we simply just plug in these two cases, and you will find that the eigenvalue equations can split into two, right? Okay. The first one, the second one. You can define properly this momentum transfer, little q, and this difference between this lattice, reciprocal lattice vector k2 and k1 as capital K. And you could simplify this eigenvalue equation for these two electron states near the degenerate point. Okay, so in the absence of U, so these two states are exactly degenerate. But in the presence of U, these degenerate point is split. As you can see that if you try to find this eigenvalue for this epsilon, you need to solve this two coupled equations. And the solutions of epsilon come from the vanishing of the determinant of this 2x2 matrix. And it is a straightforward calculation that you can find these eigenvalues as the first term and plus minus the second term. Okay? So, and you immediately see that right at the edge of this band, the crossing point, the actual say dispersion of electron states gets splitted. Okay, so they no longer meet right at that intersection point. Instead, they avoid crossing each other. So the lower band is actually bent towards the lower value than the intersection point, and the upper band is actually bent in a manner that the value is actually larger than this intersection point. So both curves represent the actual band structure after considering the Coulomb interaction or the periodic potential. So in other words, after considering the periodic potential, so you have two different bands, and they are splitted. And the amount of the splits is about 2 times this magnitude of UK, where UK is the Fourier component of the periodic potential. Okay, so in other words, if the electrons populate start from populating the lower band, and there could be either partially filled, and then this system will become a metal. However, if the electrons fully populate the lower band or the valence bands, then there is an energy gap between the valence band and the conduction band. So in that fully occupied valence band scenario, and it's difficult to kick electrons out of this upper level to the conduction band, and so that the materials show insulating behavior. So this mechanism explains pretty well how these materials show metallic or insulating behavior depending on whether this valence band is fully occupied or not. Okay, and the formation of this energy gap between the valence and conduction band comes precisely from these solutions for the Schrödinger equation for electron in a weak periodic potential, where we take advantage of this Bloch wave function of electrons, and also we consider the degenerate point of the free electron plane waves, and this degeneracy is further lifted by the presence of this periodic potential. Okay, and then we could further just find out the eigenfunction, the wave function corresponding to the the conduction band of the plus branch or the minus branch of the electron states, and they behave like a cosine or sine depending on whether the electrons belongs to the plus branch or the minus branch, and you could easily get this intensity or probability to find this electron in a particular place as a square magnitude of the wave function psi of r, which behaves as either cosine square or a sine square. And the eigenenergy associated with that state is actually epsilon plus or minus, which is just plus or minus difference relative to this free electron dispersion, epsilon 0 of q. Okay, so this calculation can be found either in Oshkov-Mermion or Kittel's first book on solid state. Okay, so this is the important calculation that you should know before we jump into the advanced topics in solid state. So this is the foundation of a metal. Right? Okay, so let's just take a short break, and when we come back, we will continue the introduction part of the solid state by reviewing this very important concept called quasi-particle and elementary excitations. Let's continue. So before we introduce the concept of quasi-particles, let me just give you a very brief review of all this, two types of particles in physics, or especially in solid-state physics. Namely, either we are talking about the fermions or bosons. I believe I have introduced this two types of particles at the very beginning of the course. But let me just go through this review one more time, because we will use this two different types of the quantum particles over and over and over again. So as you know already, that electrons are fermions, and the fermions satisfy this anti-commutation relations. For example, if I have two electrons described by this psi I and j at different spatial locations, and if I would like to interchange these two wave functions, and they anti-commute, namely this psi I psi j is actually minus psi j psi I for this two fermion system. So if I interchange the two electron wave functions at different locations I and j, and I get actual minus sign in front of this two particle wave function. Okay, so this is already, I think you should know in your quantum mechanics. And we know that electrons actually are influenced by a periodic potential, and those electrons in solids are actually localized around this ion cores, and these ion cores are periodically placed in this crystal, right? So and those systems are described nicely by these energy bands and the block wave functions that we just described. So we have the energy bands and the valence bands as a lower band where the electrons can populate first, and the conduction bands are located at higher energies. And between this valence and conduction bands, there's an energy gap, which is the order of this potential U. And the fermions satisfy this Pauli principle, and also the Fermi-Dirac statistics. And in particular, the occupation for fermions that could be observed as a function of the energy and temperature following this statistical probabilities, that is 1 over epsilon beta to the power of beta times epsilon minus mu, where beta is defined as inverse of kBt. where T is temperature. So I believe everybody should be familiar with this Fermi-Dirac statistics, which described physical electrons or other fermions. And if you make a plot of this occupation of fermions versus epsilon, or energy of that electrons, and you can see that 0 temperature, all the states below the Fermi energy mu is fully occupied with the probability 1, which means that 100% of electrons will populate at the levels below chemical potential or Fermi energy mu, and all the states are fully occupied. But at the finite temperature, only a fraction of states are occupied by electrons. At the edge of this Fermi energy, some electron actually can escape the states where they were before because of the thermal excitations, and so they will go excited, and then they become excited state electrons. So there are some missing probabilities right below the Fermi energy of electrons, and that electron states will go to the higher states above the Fermi surface. And this feature is called the thermal excitations of electrons. And the way that the electron can actually get excited from the states below the Fermi surface to the states above the Fermi surface, follow precisely the description of the Fermi-Dirac distribution. Okay? So the orange line or orange curves come from the fact that if you plug in the temperature, which is finite, non-zero, and this is the distribution of that Fermi-Dirac at finite temperature. And so the second type of particles are called bosons. And we will discuss that later in this course. But let me just introduce to you an example which you already learned in quantum mechanics that could be classified as bosons. And that example is a simple harmonic oscillator. So you must have learned this in quantum mechanics, that if you have this kind of a simple harmonic oscillator, and you could use a technique called the raising-lowering operator, and to rewrite Hamiltonian in terms of the raising-lowering operator. And that raising-lowering operator are later known as boson operators. Okay, so here in the real solid-state materials, you have a bunch of ions that could be, fluctuating or vibrating back and forth relative to the equilibrium position. So when they vibrate, they will affect all the neighboring ions. So everybody actually vibrates. So you can imagine that the lattice vibration of solids looks more or less the same as the coupled harmonic oscillator. So you could imagine that all these wavy red curves represent the springs of a simple harmonic oscillator, and everybody connects with everybody else by a spring, with a spring constant. So that this whole thing shows some kind of a normal mode vibration, and you can quantize that normal mode vibration, and those quantized energies are called phonon energies, and those energy that carry quantized values are called phonons. And in particular, we could actually construct harmonic potential of such a coupled harmonic oscillator, which mimics the realistic lattice vibration, and this phi represents this potential energy filled by some ions, and the first term of the Hamiltonian represents the kinetic energy of each ion. So the ion potential could be considered as that kind of approximated behavior that it actually go to the negative value and then starts to shoot up when the distance r between ions becomes shorter and shorter. And along the way, there is a minimum point where the ions can actually very comfortably, sit, and these ions can actually vibrate nearby this minimum point or this sweet spot, and this displacement of these ions, are defined by this vector ui, and you can imagine that each individual ion can actually vibrate with its own displacement vector, and so this is a three-dimensional coupled harmonic oscillator problem, and we could make approximation to simplify this Hamiltonian near the minimum point of such a ion potential, and if you do Taylor expansion of this potential energy phi, you could actually ignore the first order expansion because you are sitting very close to the minimum point where this this gradient term vanishes, and you could simply just expand this potential term up to the second order, which we call this harmonic potential, by taking the second derivative with respect to this displacement vector ui uj, and you sum over all such contributions. And this is where this phonon come from, and we will talk about that later in this course. And for a simple harmonic oscillator, just a single one, so the single simple harmonic oscillator like this, in quantum mechanics, you know how to actually quantize their energy. And there's a 0-point energy right here, half of h bar omega, and where omega is just the oscillation frequency. And you could, as I mentioned, use this creation of this, or raising or lowering operator, dagger on B, which is a function of linear function of this position operator x and momentum operator p. So this will be your homework problem. So find out this function, which can be used to construct this raising and lowering operator of a harmonic oscillator problem for a single harmonic oscillator, and quantum statistic of those B operator or a B quanta, and which we call this B phonon, satisfy this Bose-Einstein distribution function, and because they are bosons, and so you can see that this denominator carries -1 as opposed to this +1 for the fermions. Okay, so they behave very differently from the fermions because they satisfy different quantum statistics, and when we couple these harmonic oscillators as, say, one-dimensional chain of a couple harmonic oscillator, they'll show some kind of a normal mode vibration, which we'll discuss later, and in particular the lower branch of this phonon mode called acoustic phonon, and the upper branch is called optical phonons, and those phonons carry integer multiple of h bar times omega phonon. Okay, so in some sense you already learned phonons, but you don't know that they are phonons from the simple harmonic oscillator in quantum mechanics, and this kind of review helps you to actually pick up all the things that you already learned but you may forget already. So next time we will start to introduce ideas or concept of quasi-particles in the context of the weakly interacting electrons in solids. Okay, so see you next time.